Hey everybody, welcome to the Intro to Houdini course. I'm just doing a real quick video this time, not a full lesson. I just wanted to make kind of a mini lesson to clarify something I mentioned in the previous lesson. I got a few questions and it seemed like doing a video was probably the best way to address it. If you haven't seen that video yet, I'd encourage you to go watch it. Otherwise, this isn't going to make probably the most sense. So in part one of the attributes lesson, we learned how to create attributes and promote them. And the example we used, which we're watching right now, um, is calculating the volume of an object, which was the stand for dragon, by creating a measure stop and then summing the volume of each primitive to get the total with a attribute promote stop. So we did this because, like I mentioned in the video, it doesn't really make much sense to have the volume as a per primitive attribute, right? It makes a lot more sense to have the volume as for the object as a whole, because that's what we're used to. We're used to thinking of a volume as. But I got a really great question in the Vimeo comments section from Motion Experiments asking, what exactly is the volume of a primitive? And it's a great question because at first glance, you wouldn't expect a primitive, which is just the face of a polygon, to have a volume. But if we look at it from another angle, it actually makes perfect sense to calculate it this way. Let's think all the way back to our algebra and geometry classes. Do y'all remember the formula for calculating the area of a dragon? Well, I don't, and I don't think there is one, and if there is one, I never learned it. And I guess Houdini didn't learn it either. It's not magic. It doesn't know how to calculate the area of a dragon. It does, however, know how to calculate the area of a pyramid, and so do we. That's going to be the key to understanding how this works. So let's just switch into Houdini real quick. We're going to look at a really, really basic example. I've got a cube here. It's in wireframe mode, but it's a cube. And if we look at it, we've got a size of x width is 1, the y height is 1, and the z depth is 1. So we've got a 1 by 1 by 1 cube here. What is the volume of this cube? The volume of the cube is 1, right? The volume of a cube is just the length of one of its sides cubed. So 1 cubed is 1. We've got a volume of 1, and if we look over here in our detail view, I've calculated the total volume. It indeed says 1, and I've set this up, really simply. This is actually the exact same thing we did in the previous lesson, right? We have a measure stop calculating the volume, attribute promoting the primitive to a detail, it's summing the volume up, giving it a name of total volume, right? So we've got a value of 1, exactly what we expected. And then if we look at the primitive view, I haven't deleted the original, so we've still got the volume per primitive, right? We've got 6 faces on this cube, so we have 6 volume calculations. Each of them is being measured as 0.16 repeating. 0.16 repeating multiplied by 6 gives us 1, which is exactly what we'd expect, given that we already know that these values add up to 1, right? So the heart of this question, though, is how does it get this number, this 0.16 repeating, right? It's really the real question we're asking ourselves here for what is the volume of a primitive, right? How is it getting this number? And it's pretty cool if we look into how this works. So Houdini knows a lot of information about each primitive. In particular, it knows the coordinates of each vertex, and it also knows the center point of the object. Right? If we click our object here, we can see our handles right centered here in the origin of the object, and then it also happens to know, the location of each vertex. So using this information, it's able to calculate the volume of a piece of the geometry, right? That's using those point values. That is how it's calculating each of these numbers for the volume. So let's see how they're doing that. Let's go back to our chalkboard, which we haven't done in a while. So we're going to start by drawing a cube. just a real simple diagram here. It's not going to be exact because I can't really draw very well. Let's see. Probably the back would come up here. Oh, that's a little crooked. Okay, there we go. So we've got a cube, and let's just go ahead and mark the length, and we'll mark the width, and we'll also mark the height. Okay, now let's just focus on one face of the cube for now. So we're just going to look right here at one face in particular, right? So in Houdini, this would be called a primitive. Now, if Houdini knows the location of each vertex on the primitive, and it also knows the location of the center point of the object, it can make a rectangular pyramid out of those points. So let's see, the middle would probably be around here, the center point. So knowing the location, right, it's able to make this this rectangular pyramid shape. I said earlier that knowing the volume of a rectangular pyramid was going to be the key to understanding this. So let's look at the formula for the volume of a rectangular pyramid. And for that, we'll start by drawing a rectangular pyramid, which will be a lot faster than drawing the square. Okay, here's our rectangular pyramid. Again, we've got our length, and we've got our width, and we've got the height here. I'll just mark the height like this. Right, the height's going all the way to the tip of the pyramid. Okay. Now the formula for the volume of this rectangular pyramid is volume equals length times width times the height divided by 3. So using this formula for the area of a rectangular pyramid, let's go ahead and plug in the values from our cube that we have in Houdini. So we know that the height is equal to 1, the length is equal to 1, and the width is equal to 1. So we can go ahead and plug those values into our formula. The volume is equal to the length. So the length of the cube is 1, but the length here in this rectangular prism is actually kind of translated to the height in the diagram we drew. But it doesn't really matter that much. The length here of the whole side of the cube is equal to 1, but this is the center point, right? If we drew it all the way down and then out to the edge, it's actually just half of the length. Okay, so the length right here, this measurement, is just going to be 0.5. So 0.5 multiplied by, what is the width? Well, the width is just 1. That's pretty easy. You know what? Let's go ahead and move this down a little bit, just to make it a little easier to see. Okay, 0.5 multiplied by 1, and then what's the height? Well, the height right here is just 1, so multiplied by 1 again, divided by 3, and this formula simplifies to 0.5 divided by 3. And if we go ahead and divide 0.5 by 3, we get 0.1666666, repeating, so on. So indeed, what Houdini is doing to calculate the area of a primitive is it creates a pyramid using the vertices of the pyramid and the vertices of the primitive, and the center point of the object. That's why we can calculate the total volume of a piece of geometry by summing up all of the primitives' volumes. Each pyramid, in this case, perfectly fills out the volume of the cube. So let's look at it inside of Houdini just to kind of drive the point home. Now I've gone ahead and added some lines connecting each point of this cube to the center point of the object. So I'll just enable that. Right, so this should look really similar to the diagram we just looked at, except instead of just drawing one of the pyramids, we're looking at all of them here. So let's make sure we have the primitives view open and we can look at the individual volumes. Again, nothing's changed. We have 0.16 repeating right now. But if we select one face and move it around, so I'm going to select one face here in the edit, make sure I've got the attribute promote selected so we can actually see our attributes here. I'm just going to slide this face along. And we can see that our values for the volume change in the geometry spreadsheet. We can see actually exactly what's going on. One value hasn't changed, the fourth primitive. It's still got a value of 0.16, which it shouldn't because its pyramid hasn't changed sizes at all, right? If we look at the cube again, this the rightmost pyramid that we have here is exactly the same size as before, since we've moved the face. Now 4 of these values, 0, 1, 2, and 3, they're exactly the same, which again we would expect that because even though they're all getting, squashed and stretched when we pull this face, they're all changing uniformly, right? The top, the bottom, and then the front and the back faces here, right? They're all changing exactly the same, so we would expect their volumes to all be exactly the same. And then the final value for this fifth primitive that we have selected here, we can make it get really big or really small depending on how close or further away from the center point we slide this face. Right, so if we take the face, push it real close to the center point, we get a really, really small volume, and right, everything else is kind of changing accordingly. Now, let's think back to the dragon. There were a lot of negative values for the primitives volumes, and how in the world can we have a negative volume? We're going to take a look at that too. So if we take this face and we move it past the center point, we go ahead and deselect it there so we can see a little more easily. Now we've got something kind of interesting looking, right? We've got a center point that is actually outside the geometry, and all of the pyramids here are looking kind of different now. Instead of meeting up in the center point, the center point happens to be someplace not inside the boundaries of the object, and we can see that our fifth primitive actually has a negative volume here. Now this actually makes sense too. Otherwise, we would end up adding total volume to this model by making it smaller past a certain point. So in the case of pyramids that are flipped inside out, like this one that we have for this fifth primitive, the volume is negative so that it can be subtracted from the sums of all the other positive polygons. And when we did this with the dragon, it was the exact same process, only done many, many, many more times. Now, granted, we've done this with a cube, which is going to give us pretty precise results. The dragon actually has Dragon's got a lot of curves, bumps, divots, right? A lot of complex shapes in the geometry. So actually, the volume in the case of the dragon here, it's going to be more of an approximation than an exact specific value, but it's still going to be a very good approximation. So that's it for this video. I hope it's clarified a few things and hopefully got you thinking a little bit more about how Houdini operates under the hood. I think you'll find that if you take a closer look at things that seem complicated at first, you'll find that they're actually quite simple on a fundamental level. Again, thank you, Motion Experiments, for asking this question about volumes per primitive. I'm getting a lot of really good feedback on these videos, so I'd encourage you guys to leave a comment letting me know what you think or asking questions if things are unclear. So if it seems like an interesting enough topic, I'd really like to make more videos about it. Because I think that having this kind of dialogue back and forth can be really great to help everyone understand Houdini better. And the better we can fundamentally understand what's going on under the hood, the more powerful the tool becomes. Oh, and one more thing, because I know I'm going to get questions asked about how I drew these lines if I don't go into detail. So let's go back and look at the box real quick. Let's see, make sure nothing. Okay. Let's go back to the box. Oh, doesn't really matter where the points are, but I'll go ahead and put the box back to its neutral state here. So after this attribute promote, I have added a curve stop, and in the coordinates I put a quick expression. So just right click it, go to expression, edit string, and then you can see the expression that I've put in here. I've referenced the object's center point, right? The channel reference to the box, and then its x position, the y position, and then the z position. And then the second point on the curve is referencing point 0, point 1, point 2, and so on from the box. So it's got 8 points, so that's point 0 through point 7, representing one of each of the corner points on the box here. And this expression here, right, it's probably not the most efficient way to write this out, but it was a very quick way to write it out. So, and after that, I just added this primitive SOP to give it the color, because when it was just a curve, we weren't getting any color, right? The lines were just black, and I thought that if we, made them orange or something, it'd be a little easier to see. We haven't looked at the primitive SOP before, but it works exactly the same as the point SOP, only for primitives instead of points. I just added color here. So, okay, so that's really the end of the video. Thanks for watching. Thanks for asking questions. Thanks for engaging. I really, really enjoy making these videos, and I really enjoy, getting to talk back and forth with people who are also enjoying them. So, stay tuned for the next video. Take care.